Hello, my name is Hwan Kim. I am very pleased to present my paper at this conference. The title of my paper is Design and Implementation of a Real-Time Anomaly Detection System based on YOLOv4. So, let's start the presentation. The table of contents of the presentation is as follows. First is the introduction. With the advent of Industry 4.0, new changes are coming to the manufacturing industry as IT technology develops. The application of smart factories based on innovative technology for manufacturing competitiveness cannot be delayed any longer. Smart factories are meaningful in that they meet various customer requirements and improve production efficiency by collecting and analyzing production information in real time for the manufacturing site. By breaking away from the existing mass production method. After COVID-19, the preference for non-face-to-face work and the rise in labor costs have made it difficult to secure manufacturing manpower at the manufacturing site. Recently, to solve this problem, there is a demand to entrust the product quality inspection task to an AI-based vision inspection system. The task of determining whether a product is defective requires high accuracy. In addition, appropriate costs must be calculated at a level that can be introduced even by small and medium-sized businesses. Therefore, a low-cost and efficient system is required. This study is YOLOv4 based on the anomaly detection inspection method. It inspects objects moving on the conveyor belt in real time and aims to determine whether the object is good or bad and classify products. The proposed system meets the level of product defect inspection required by actual manufacturing sites. It can be expected to have the effect of improving productivity and the operating costs of the company. In addition, it aims to link the system to the MEMS and ERP systems used in the factory by building the system on an edge computing device. The established system supports the monitoring system to adjust factory production schedules or respond to emergencies using the collected data while collecting manufacturing data. Through this, it contributes to building a smart factory that can be controlled remotely, and a deep learning training model can be applied in real time in a cloud environment. And uploading the collected data contributes to building a manufacturing data platform so that manufacturing data can be used more innovatively. Next is the related work. Anomaly detection refers to the problem of distinguishing between normal and abnormal samples, which is actively being addressed in the manufacturing industry. When both normal and abnormal samples are labeled in the given training dataset, it is called the supervised learning method, and the model learned in that method teaching object discrimination. It is called supervised anomaly detection. This method is mainly used when high accuracy is required. It is possible to derive higher performance by having a variety of normal and abnormal samples. In the case of semi-supervised learning, it means that only normal classes are defined and learned. This can be useful when you want to detect a class other than the normal class. In the case of unsupervised learning, no class is defined and only images are learned to induce the deep learning model to make its judgment. As a separated class is not defined, the learning image aims to use only the normal class or train only the bad class. However, it is recommended to train only one class of images to be learned. In this paper, supervised learning is applied among two above concepts. There are many cases when only one type of defect class is not defined, and each defect type has a different method to be taken on site. For example, if a product is not cut correctly, it may be necessary to correct the cut. Likewise, if the color of the product has changed, the material of the product may require checking the injection temperature. In addition, statistics on what kind of defects should occur or not should be available, and since high accuracy is required, therefore, supervised learning was selected over semi-supervised or unsupervised learning even if there were difficulties in learning. You only look once. YOLO is a state-of-the-art real-time object detection system. RCNN, which is a representative object detection, uses region proposal when learning images about 2,000 are created and learned, which consumes a lot of time and resource for learning speed. To compensate for the shortcomings, the YOLO model has emerged and real-time, high-quality, reliable object detection result can be obtained with only a single GPU resource. The image acquired on the conveyor belt must be discriminated in real time, and the discriminating result must be delivered to the discharge unit. In addition, a long learning rate may interface with the input of the field that change flexibly. Therefore, in this paper, the YOLOv4 model with fast learning speed and discrimination speed was adopted. Edge computing refers to performing computing at or near the physical location of a user or data source. By processing computing service at a location close to the users and device, users will receive faster and more reliable service, and businesses will benefit from flexible hybrid cloud computing. Edge computing is one way for enterprises to distribute data computation and processing in multiple locations using a common pool of resources. Image learning can be performed in the cloud or on a remote server. However, if image identification is performed through a remote server or a cloud server, product identification and communication with the PLC may not be performed smoothly due to network speed and various variables. Accordingly, in this paper, an edge computing device was built next to a conveyor belt where products are produced. In addition, it may be difficult to prepare a separate learning server in a small-scale factory. Accordingly, a device capable of learning images was prepared. Additionally, the monitoring user interface program was prepared to be executed so that the user can check the determined image in real time. The device is connected to the internet and is ready to be linked to the factory's MES ERP system at any time. In addition, a system that can remotely check for product defects at the site and instruct production, suspension, and change the product in real time has been linked. The confusion matrix is the basis for determining how accurate the learning of the AI model is. To understand the confusion matrix, you need to understand four concepts first: true positive, TP, predicts that an answer that is actually true is true, correctly answered. False positive, FP. Actual false predicts that the correct answer is true, incorrect answer. False negative, FN. Predicts the correct answer that is true as false, answer incorrect. True negative, TN. Predicts the correct answer that is actually false as false, correct answer. It shows intuitively. Recall or sensitivity, as it is called in psychology, is the proportion of real positive cases that are correctly predicted positive. This measures the coverage of the real positive cases by the philosophy predicted positive rule. Its desirable feature is that it reflects how many of the relevant cases the philosophy rule pick up. Conversely, precision or confidence, as it is called, is data mining, denotes the proportion of predicted positive cases that are correctly real positives. This is what machine learning, data mining, and information retrieval focus on. In this paper, we will apply the concepts of precision and recall to determine whether products identified by deep learning training has been accurately classified. For accurate learning and classification of deep learning models, the object model evaluation must be performed by crafting the corresponding concept. While global manufacturing is becoming more competitive due to varieties of customer demand, increase in production cost and uncertainty in resource availability, the future ability of manufacturing industries depend on the implementation of smart factory. With the convergence of new information and communication technology, smart factory enable manufacturers to respond quickly to customer demand and minimize resource users while maximizing productivity performance. In addition, there are also cases where new smart factories have been established based on manufacturing data in interesting companies that focus on the personalized cosmetics manufacturing industry. Manufacturing data is now attracting attention as useful data that cannot be discarded in the first industrial era, and it is important to secure data collected in all production processes. It collects good and bad production or products through edge computing equipment. It also collects product production information and set information. It can be used to build a manufacturing data platform using the collected information and apply it to build an artificial intelligence-based smart factory system. From now on, I will explain the YOLOv4 based real-time anomaly detection system proposed in this paper. The figure shows the concept drawing of the system proposed in this paper. Due to the reflection of light due to the material characteristics of the inspection product, since diffuse reflection occurs, it is configured in an indirect lighting type that minimizes light reflection for optimal optical system configuration. In order to avoid diffuse reflection of the product, the shooting angle of the camera was corrected by 2 to 5 degrees so that it was not perpendicular to the product. When the proposed system is run through edge computer, the installed camera continuously acquires images with software graph. In the acquire area, check that the product is detected using a half circle transform. When a product is detected, the coordinates of the photograph product are calculated to check whether the product passed through a discernible location. If the product passed through a discriminable location, the run YOLOv4 model determined whether the product is detected. The determined image and result are output from the separately implemented monitoring system. The determination result is transmitted to the discharge cylinder. Since the discharge cylinder only moves the cylinder according to the electrical signal of the program, after storing the determination result in the edge computer's determination program, when the determined product passes in front of the cylinder, the product determination result is transmitted. As a result of the transfer, the defective product is pushed through the cylinder to be moved to a different conveyor belt line than the normal product. To prevent future damage to other normal or defective products in the process of pushing the product, a sponge is attached to the cylinder to alleviate the impact when the cylinder and product collide. Following are the experimental results. The test site was conducted on a conveyor belt where actual products are produced. The table above describes the hardware list used in the design of the system. An ACA 1360GM mono camera sold by Basler was used as the camera, and a 16mm C-mount lens sold by Tamlons was used as the camera lens. The monitoring system and the edge computer that performs deep learning and image discrimination was prepared with the same specifications as above. For optical system lighting, two LED bar lights were used. As I explained in section 3, since the inspection material of the product is a sticker, reflection occurs when light shines directly on the product, so the image is not accurately acquired. Therefore, by correcting the angle of incidence of the light illuminating the product is induced to be illuminated with in-direction light. In addition, when the camera shoots a product vertically, light reflection may also occur. So adjust the angle of the camera so that light reflection does not occur. The figure is a picture prepared to understand the above explanation. In the case of the product on the left, a reflection of light occurred, so the left and bottom sides of the sticker, which must be identified, are not visible. In addition, reflection occurs in the center of the sticker, making it difficult to accurately detect the defective class. On the other hand, in the case of the product on the right, there is almost no light reflection, and especially the area of the sticker that detects the defective class is accurately illuminated. The specification of the product used and the shooting environment and introduced in the table above, and the learning label class can be checked in the figure above. The normal class was not learned separately, but was learned in three classes: sticker, field off, winker sticker, winker, and out of position, escape. The reason for not learning the normal classes is that the product's bad class features often include the characteristics of the normal class, so good performance was not obtained as a result of learning the normal class. Therefore, Only images of defective products were defined and trained without learning the normal class. Of course, even if normal class and defective class were detected together, it could be classified through programming. But as a result of the experiment, the accuracy of the system was measured to be higher when only the defective classes were learned. Cosmetics container to which this paper applied goes through the sticker attachment process after the injection process. If the location of the attached sticker is not correct, if the surface of the sticker is damaged and an image different from the normal product is taken, the product passed through the discharge cylinder to a different discharge unit than the normal product. The video is a picture of the setup system discriminating between defective products and normal products based on the above description. Based on the defined class, the learning train was performed of the YOLOv4 model. 1 week from initial data learning to final inspection took time, and a total of 5 inspection courses were conducted and before the experiment. It was trained using about 3,000. The reason for studying the learning failures was to examine whether the accurate performance could be achieved even in a short learning failure. As a production process is focused on small lot production of various products is highly demanded, it may be difficult to apply the requirements of variable field if a lot of learning time is required. Accordingly, to achieve maximum performance with minimal learning, the learning image and learning time were set to be small. In the case of early learning, due to the difference between abnormal samples and data and actual test data, a normal product was judged as defective over detection, or a defective product was judged as normal misdetection. However, as the amount of learning of bad sample data and normal sample data gradiently increases, it finally shows precision 1 recall 0.996. Table is tabular summary of the experiment result. Since the bad classes was learned in this experiment, FP corresponds to detecting the bad class in a good product. Conversely, Fn is a case where a defective product cannot be detected as a defective class and is judged to be a normal product. You should look at the table with this in mind. For example, in the first inspection, 130 products were prepared and 85 defective products were included. Here we detected 52 defective products, and checking the products that were identified, 33 defective products were identified among the products that were determined to be good. So, there are 33 FNs. Conversely, among the products identified as defective products, there were 0 normal products, so FP will be 0. Now, according to the calculation formula, precision equals TP divided by TP plus FP. So, precision equals 52 divided by 52 plus 0 equals 1 is divided. For recall equals Tp divided by Tp plus Fn, which leads to recall is called 52 divided by 52 plus 33 equals 0.61. Viewing the table in this way will help you understand. Now the conclusion. By using the designed real-time anomaly detection system, it was possible to reduce the number of people put into the inspection department in the field. It was possible to achieve the result of enduring the fatigue of the existing workers. In addition, it has great significance that it has established a model that can be applied immediately in the field at a low cost. Since this system is a model created based on supervised learning, it is essential to collect bad sample data, and good performance cannot be achieved unless variable data and secure as shown in the table in the previous slide. Uh, Accordingly, the goal is to review the GAN model and study an anomaly detection model that can be satisfied in the field even with unsupervised learning so that the data is produced by artificial intelligence and used in learning data. This paper does not give specific suggestion of how to utilize the collected manufacturing data. There are infinite ways to utilize manufacturing data, and as a representative example, research to implement a predictive maintenance system using manufacturing data in the smart factory industry can be confirmed. As the number of products produced increases, the amount of data collected is vast, so big data basis platform research is also being prepared, and it is attracting attention as data that can be used in variable other systems. If raw data collected in small factories can be transmitted to cloud, MES, or ERP servers using a simple system, it is judged that it will be helpful for applied research using this. This concludes the presentation of this paper. Thank you.